So, last class we have seen that if you have a system, physical system is there, and if there is any perturbation is there, and that perturbation we have considered in additive perturbation form, then we can convert that system into general P delta structure. Since in our case is the additive perturbation, so our structure is P delta A, it is not M, it is A, P delta A structure. So, then we have seen that P is a P M is the 4 by 4 block. So, it is also called 4 block representation of a dynamic systems, where the perturbation is taken out from the system in the outer loop. So, if you see the basic structure of, there are two loops are there, the two outer loops, one is the upper outer loop and another is the lower bottom or lower upper lower loop. So, if you are interested to merge the perturbation block into a P block, then we have to eliminate W from this expression. So, ultimately you are eliminating W, we got this expression. Then you got it this expression, that the relation W Z, then U this, that P delta structure in P block, the delta, the perturbation block is entered here. So, how will you get it? Remember this relationship between output and the input, this, that since we are the outer loop is merged to the P block, then P block last row, that means P 22, it will start with P 22. So, it is a first index P 22, then next will be P 21, then delta A perturbation bracket I, what is called I is identity matrix of proper dimension, then P 11, then delta A whole inverse. So, this first index already came. So, the second index will come last. So, it will be a P 12 multiplied by this. So, it is called the linear fractional transformation LFT. Since the upper block is merged to a P block, so it is called upper linear fractional transformation, this one. Similarly, if you like to that lower loop, if you want to merge to P block, okay. So, naturally that change P block will be a function of the controller K. So, that will be called, again it is a linear fractional transformation, but this upper, that lower block is converted into a, is merged into a that block P block. So, it is called lower LFT. So, now we will consider that lower LFT, how to get it the lower LFT. So, in order to get the lower LFT, that means in turn we will get the transformation between Z and W, between W to Z. W is the exogenous input and Z is the regulated output, exogenous input, and this is the Z is the regulated output. So, let us see from the basic equation we can write Z is equal to P 11 W, P 12 U, and Y is equal to P 22 W plus P 21 W, P 22 U. Then from this equation, let us call this is equation number 1, this is equation number 2, and in addition to this we know another equation that U is equal to K into Y, that is that one. If you see this basic diagram, that one, this one K into S, K, I am omitting the S for convenience, this K into Y. So, now after manipulation we will find out the relationship between W and Z. Input is W and Z. So, it is a transformation between the signal W and Z. So, you can write now, if you use this one, I can write this one, Y is equal to P21 W plus P22 K y. So, if you bring it that side, it will be a I minus P22 K of y. I am bringing to that side, then P21 W. So, therefore, y is equal to that I minus P22 K whole inverse P21 W. So, let us call this is equation number 4. Now, from equation 3, let us call this is equation number 3 that I missed. So, from equation 3 we can write it now. From 3 we know u is equal to k into y. We already know the expression of y. You see, expression of y is this one, you will put it there. So, it will be a k into I minus P22 k whole inverse P21 W. So, replacing u in from equation 1, from 1, then only we will get the relationship between the input signal W and the Z. The regulated signal Z and the input signal is W, which is exogenous input. That relation we can find out. From there we can find out the transfer function, and that transfer function is very useful when we will design the H infinity controller for a dynamic system in transfer function domain. So, from 1 we can write Z is equal to P11, you see, then W, then P12 U. Put the value of U, P11 W, P12 K, then I minus, I am putting the value of U, I minus P22 K whole inverse P21 W. So, if you take the W common exogenous input, so P11 plus P12 K this, then I minus P22 K whole inverse P21 into W. So, this whole thing is nothing but a function of our P block and K is W. So, this we denoted by the transfer function, this one you see Z and W. Z is the W is the input, Z is the output. So, it is the transfer function between the Z, W and Z. So, it is denoted by transfer function between input and output Z, this into W. So, what is our transfer function between this and this? T Z W between the input and output is equal to P11 plus P12 K I minus 22 K whole inverse P21. So, this is our transfer function, and this transfer function is very useful when you will design the H infinity controller. Then you have a, how you remember this expression? You see, as I told you earlier also, look the basic block 4 block representation of system. Agree? So, this loop, the outer loop, that 4 block, the lower loop, we want to merge it in P block. So, you want to merge in P block, that means you have to start with the upper row of that P block P11. So, I have started with P11, then first index I have written, then P12, another index is left with P12, then controller, then I minus. So, P11, so it will be P22 K whole inverse, then it will come the what is called second index last. So, first index it has come first and second index will come last. So, it will be a P21. So, this is the transfer function of this one. So, we know how, first thing we know how to represent in general, if you have a dynamic system is there are basic 2 inputs, 2 output. One input is exogenous input, which consists of that noises, then disturbances, then command input, and the another input is control signal input, which will regulate the system response. So, output we have a Z, that is called regulated output. That output is affected by W. Okay. That regulated output may be a state, error, then your may be a control signal, all these things. Then another is your Y. Y is the output, that is the measured output. That output will be used for controller design to regulate the system response. So, this is the basic block diagram structure. So, any system we can represent into 4 block representation, in the sense that any system we can represent by W, U, Z and Y. And if there is a perturbation is there, perturbation block will come here, agree. And if your controller is there, controller is connected to be here, the K of S, and this is the perturbations. So, this is the basic structure of the. Before we go little bit details in the H infinity controller design, we must know what is the frequency response of multi input multi output systems. So, next is our discussion is multi input multi output system response, frequency response, frequency response of a dynamical system GS bracket multi input multi output system. We have discussed little bit single input single output. We know in undergraduate class also what is single input single output. So, briefly I will discuss first frequency response of single input single output. Suppose a dynamic system is there, which is described by a transfer function model GS. So, I want to get the frequency response of this one. So, and you assume the system is linear, time invariant system. The frequency response is this one, that your input is a sinusoidal signal, magnitude of the input is kept constant, then frequency we are changing. At each frequency we will see what is the output magnitude, and frequency will be same, but there will be change in phase angle. Each input or each frequency will observe that one. So, let us call our input is, we have, since you have a frequency response u 0 sin omega t of alpha, this is the input. So, naturally our output response also will be sinusoidal, but magnitude is different from u 0 and phase angle will different from B. So, let us call this will be u 0 magnitude of g j omega of this and sin omega t, same frequency, mind it, and beta. So, where g of j omega magnitude is nothing but a gain of the systems, gain of the system at frequency omega. So, naturally from this expression you see how I am telling it is gain, I will explain later here. Now, you see it is dependent on frequency. Okay. So, what do you mean by the gain? At a particular frequency, what is gain? Input magnitude is u 0, output magnitude is, this whole thing is y 0. So, what is gain of this one? Y 0 by u 0. So, this y 0 by u 0, if you do this one, it is nothing but a g of j omega. It represents the gain of the systems. So, gain of the system, it does not depend on the input, because u 0 output is u 0 g j omega and input is 0, u 0 constant. Whatever the input magnitude is changed, corresponding output magnitude is will be changed. This is the property of linear systems. and phase angle the frequency will be remain same, input frequency, only phase angle is changed. So, that you can say output amplitude of the signal, output amplitude of the signal divided by input amplitude of the signal. So, it is basically it is nothing but a g of j omega. So, and what is the phase angle associated with this one? We can easily see phase angle associated with g of j omega is angle associated with g of j omega is nothing but a beta minus alpha is the phase shift. Now, how will you see? We know the phasor quantity. What is this? If you represent this phasor quantity, I can say that one is something like this way. This is u 0 u of t is equal to u 0 sin omega t plus alpha. If you represent it in a phasor quantity, means a vector which is rotating with a constant angular velocity omega. This is also another vector which is rotating with a constant velocity omega, both are same. So, I can say this I can represent it by this one u 0 e to the power of j alpha, and this is the vector. And how will you represent this vector? Magnitude is u 0, phase angle is, it is something like this, magnitude is u 0, phase angle is alpha, and that vector is rotating with the angular velocity omega. You can say this is the real and this is the imaginary axis of this one. How will you represent that one? Y 0, that y of t is equal to y of 0, you know y of 0 is what? This part is y of 0 sin omega t plus beta. So, how will you represent in phasor quantity form? This is will be y of 0 e to the power of j beta, and that vector is rotating with the angular velocity omega, and that phase angle is, you can think of it as maybe like this way, this is your u 0, this is y 0, and phase angle is beta, and that is also rotating with the angular velocity of this. So, if you see this one, ratio of these two phasor quantities of this one u 0 y 0, agree, and phase angle will be beta minus alpha, is nothing but this one. If you see y 0 e to the power of j beta, this is the output signal phasor quantity, and this is u 0 e to the power of j alpha, which is equal to y 0 e 0, and this is nothing but e to the power of j beta minus alpha. So, its magnitude is, if this is a gain is nothing but this quantity is nothing but if you see the g of j omega absolute value, this gain, and what is the phase angle associated with beta minus this. So, this is the what it means in a linear system for single input signal, the input signal is changed by a factor. You see input signal u, output signal is what? The input signal u magnitude is changed by a factor, this factor, agree, and its phase angle is changed by a angle. So, I can write it when this signal, you can say when signal u t is passed through a system, agree, the input magnitude signal is changed by a factor u 0 by a factor of that one, agree, and its phase angle is changed and it is see, and its phase is shifted from input by phi, which is equal to beta minus alpha. Okay. Now, let us kill this extent, this concept can be extended for a multi input multi output systems. So, let us scale for multi input multi output systems. So, what is this? We have a systems GS, and GS is a multi input multi output system. So, let us call the number of outputs is P and number of inputs is M. So, this is a transfer function matrix, not a transfer function only, transfer function matrix, and P stands for number of outputs and M stands for the number of inputs. So, you can think of it if more than one inputs are there, if I represent by double line to differentiate from this one, that is u of t, and its magnitude is what is the how many input vectors are there, input vector dimension m cross 1, or in Laplace domain it is a u s, which dimension is m cross 1, and output is y of t, whose dimension p cross 1, or in transfer function domain y of s is a p cross 1. So, if you write the transfer function matrix relationship input output relation, we can write it y of s is equal to g of s into u of s. You cannot write for multi input multi output say transfer function y of s divided by u of s, because y in your case is a vector p cross 1, this is m cross 1, and in turn this will be a p cross m. So, you cannot divide that one, you have to write into this section some transfer function matrix multiplied by input is equal to output vector. Some transfer function matrix multiplied by input vector is equal to output vector. So, this is the expression for this one. Now, let us see this. So, if you write how many outputs are there, p outputs, how many inputs are there, m input. If I write more in general vector and matrix notation form, we have a how many outputs, p outputs are there, y p of s is equal to, and how many the g of s, what is the dimension, p rows m columns, m columns. So, g 1 1 s, g 1 2 s dot dot g 1 m of s, g 2 1 s second row, g 2 2 s and g 2 m s, and in this way the last output expression, this is first output, second output, this last output p means last output in pth output is equal to p into p 1 p 1 s g p 2 s dot 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 g p m s, that multiplied by input vector. How many input vector dimension is how much, u 1 of s m, u 2 of s dot dot u m of s. So, this is the basic equation of this one. So, that vector is the input vector and that is the your output vector, and this is our transfer function matrix whose dimension is p cross m. So, this is you can call input channel vector, input channel, and this is your output channel. So, input channel ith component, that is first component, second component and ith component. If you write it this thing. So, now look at this one, what is y 1 s? Y 1 s is nothing but a g 1 s u 1 s plus g 1 2 s u 2 s plus g 1 3 s u 3 s and so on plus g 1 f u s. So, if I write it that ith, that output channel ith component of ith channel, ith component output of the ith channel. So, if we write it, the ith component of output channel. How I can write it? W y I of W is equal to G I 1, because it is the ith component. Ith component start to G I 1, G I 2, G I m. So, G I 1 of W, G I 1 of W, U 1 of W, then G 2 of W, G I 2 of W, U 2 of W plus dot dot G I m of J W. So, I missed it J and this y I of J. S is replaced by that this one. So, you write it J. So, this is the ith component, and I varies from 1 to dot dot P, because there are output channel, there are P outputs are there. So, we can write it this summation of I is equal to, or J is equal to 1 to m G I J omega U J omega, this one, where U J omega is nothing but a, you see what is this one, I can represent this is a nothing but a what is called phasor quantitative form. This is nothing but a U j 0 e to the power of j alpha j. First component, let us call first component U j U 1 of t, what we can write it? U 1 of 0 sin omega t plus alpha 1, and in phasor quantity what will write it? I will write it U 1 0 e to the power of j alpha, and that vector is rotating with the angular velocity omega. So, this is because this is a function of omega at the imaginary component of this vector, imaginary component of this vector represents that one. If you see, this is that vector U 1 0 e to the power of j alpha, and it is rotating with the angular velocity omega, and this is real and this is imaginary part, and imaginary component, the vertical component of this one is nothing but this. So, this is a function of omega. Omega is changing, omega is going, is the constant speed. So, I can write it G j omega is that one, and for and similarly y I j omega, I can write it y I 0 e to the power of j beta, agree, beta I, agree, and this is j varies from 1 to dot dot m and I varies 1 to dot dot p. So, how many vectors are there? Phasor vectors, there are m vectors are there. How many output vector, how many vectors are there? I mean, there is a output vector, output channel vector is there. How many components are there? P components. The input vector, how many components are there for the input vector? M components. So, input vector dimension m cross 1 and output vector dimension p cross 1. So, we can write it, this is a, if you write it this one, this is a function of, this is not j, this is a function of this. So, I can write it that one, that u of w is nothing but a, u of w is nothing but a u 1, agree, u 1 of w, u 1 of w, u 2 of w dot dot u m of w, and which we can write it, what you can write it, this one, you put the value of u 1 or w, that is your u 1 of 0 e to the power of j alpha 1, u 2 of 0 e to the power j alpha 2, and so on u m of 0 e to the power j alpha m. So, this is the case. Similarly, I can write u whose dimension is m cross 1, this dimension is p cross 1, which is nothing but a, this is the phasor quantity of this one, I can write representing that one, and this is I write in y 1 0 e to the power j beta 1, y 2 0 e to the power j beta 2, and so on y p of 0 e to the power j beta p. Agree? So, this is our input vectors, input. So, this is you can write it, this one it is a input vector of sinusoidal signals. This is the your output vector of sinusoidal signal. Okay. So, we have represented them. Now, this is a complex number. So, this is a complex number representing this one, you see this is the complex number, u j is a complex number. Similarly, y x is also complex number representing at each frequency omega, representing at each frequency. Why I made it frequency? If frequency change, because we are frequency response, when frequency we are changing, keeping magnitude is constant. So, the vector will be that u I y 0 of this one, this will dependent on the frequency of that one vector. So, this is changing with a that is rotating with a angular velocity frequency. Suppose supply frequency is omega 1, it will rotating with a angular velocity omega 1. If supply frequency is changed from omega 1 to omega, it will rotate with a angular velocity omega 2. So, this is that is why it is written function of omega. So, now we can write it this expression. What is the magnitude of the input vector? What is the magnitude of input, but a complex quantity magnitude is what? If the complex number is there multiplied by its conjugate, then take the square root of this one, or you know the magnitude of this one is nothing but a u 1 square of this one. So, our vector is that one. This is the input vector. I want to find out the magnitude of the input vector. So, magnitude of input vector signal u of w, again u of w. What is this one? Magnitude is nothing but a vector is nothing but a Euclidean norm, is nothing but a root over u 1 0 square per u 2 0 square plus dot dot u m square of 0. Suppose you consider this one element. What is this one? Magnitude of this one u 1 0 square, but it is a vector of m elements. So, individual square, sum of individual square plus square root of that one. Okay. So, this is the magnitude, or you can say u w into u star transpose, that will give you the magnitude square, that I need magnitude. So, it is nothing but a Euclidean norm of this signal, this one. Similarly, magnitude of output vector signal y of w is equal to y of w Euclidean norm distance two norms or Euclidean norm. Euclidean norm is equal to square root of y 10 square y 20 square plus dot dot y p 0 square. Agree? So, what is the gain? You have applied input vector to a system, m inputs we have applied system and we got it output is y vector p vectors. So, what is the gain of the systems? The output we know, input ratio of this one is the gain. So, the gain of the system G s, which is p cross m systems transfer function, gain of the system in transfer function matrix is for a particular frequency particular input vector u of w is given by norm of the input vector magnitude, that vector magnitude is a gain, or you can say physically it is not a energy contained in the output signal divided by energy contained in input signal is a gain. So, this is just now we have seen this is nothing but a g of j omega into u of j omega of this divided by this is our output, agree, and this is equal to u of omega of this. And just now this is nothing but our, if you see this is nothing but a y w of t, I have written this one, u of w as it is this one. So, this is nothing but a square root of 0 1 0 square root of second output square magnitude square, then dot dot plus y p 0 square whole divided by square root of u 1 0 square plus u 2 0 square plus dot dot u m 0 square this. So, this is nothing but a gain. You can think of it, suppose we have a two signals are there, sinusoidal signals, and these two signals if you add together, then what is the energy content in this signal is nothing but a square root of RMS, that RMS square of individual signal RMS square, sum of RMS square. It is something like this only, because you have though it is a maximum value, I can divide by what is called root 2 square both side, then it will be RMS only. So, the gain of the system is nothing but a, for multi input output is nothing but a input output vectors, magnitude of output vector and magnitude of the input vectors. Look at this expression, this is a dependent on frequency, the gain is dependent on frequency, same as the single input single output case. In addition to that, we have another freedom, that the gain also depends on the direction of the input vector, that we will see later. So, we can say remarks again, the gain depends on the frequency and independent of magnitude independent of the input magnitude, input vector that means u of w of this. Further further it also for multi input multi output case, the gain depends on multi input gain depends on the direction of input vector, direction of input vectors, input vector u of t m cross 1. So, this is another freedom, in adjusting the rather in order to change the gain of the system. So, this is an additional freedom, additional degree of freedom to have different gain of the system, to control the gain of the system, to control the gain of the systems. So, multi input multi output we have another freedom, it depends on the direction of the vector, the gain of the system also depends on the vector what is called the direction of the vector, and also it depends on the frequency. But in a single input, because there is only one input is there. So, it depends on the gain depends on the frequency. For multi input it depends on the frequency, we have another freedom to control the gain of the systems, that is the direction of the input vector. So, let us see now how to get the so, as I all these things background we have to give it before we discuss the what is called design of H infinity controller. So, next is singular value decomposition. In short, it is written SVD. So, singular value decomposition is there. I am just instead of writing this one. If you have a matrix is a non-square matrix is there, this matrix may be real or complex. This matrix we can decompose into 3 matrices, M cross M one matrix, then sigma whose dimension is M cross n. What is M first? That first matrix will be M cross n. Then what is the second matrix? It will come the dimension same as that one. Then third matrix is your B transpose n cross n, the dimension of that one. So, for real matrix A, which is rectangular, this matrix is your orthogonal matrix, orthogonal matrix. You know the properties of orthogonal matrix, and this is the rectangular matrix, agree, and this is also orthogonal matrix. But if it is a complex matrix is there, then this matrix, if it is a complex, so I am writing in the black complex or sorry blue, then this matrix will be a unitary matrix. The complex matrix instead of orthogonal matrix, to differentiate that one, it is a unitary matrix, and that is also unitary matrix. and in that case we have to write, this is I am writing in bracket u sigma V h, and V h is the unitary matrix, this agree indicates. This indicates V is a complex thing, conjugate then transpose, V h indicates. So, note that V h indicates that V star transpose, and so any real matrix or complex matrix I can decompose this into this form, 3 matrices. In real case it is the orthogonal matrix, V and U are orthogonal matrix, and this is a rectangular matrix, agree, and each elements are real. The elements of this one are real, and this rectangular only diagonal elements are there present, only diagonal elements are present, and only diagonal elements are present. Whether it is a complex or real, is diagonal elements present and that are real, both cases. So, there are few properties are there statement to, from this one we can make few statements. The following statements, are true. It is obvious, you look at this one, look at this. Since it is a orthogonal matrix or Hermitian matrix, we can write it, let us call real matrix, A is a real matrix. What we can write it for this one? You see, the columns of U 1, the columns of U m cross m are the eigen vectors of the matrices of the matrix A into A, and for if it is A is a complex matrix, then it will be A into A h, if it is a complex. What is A h? A h is the, if A is a complex, H in A conjugate transpose. This indicates, H indicates, the bracket is considering when A is a complex. This indicates is nothing but A conjugate transpose is equal to A H. Agree? The columns of U are the eigenvectors of the matrices. This is the, and this is obviously true. How? You see this one U, I multiplied by, suppose real case, I multiplied by A into A transpose. A is U sigma V transpose, this is A. A transpose is what? Reverse order, V sigma transpose, then U transpose. Now, you see U sigma V transpose B sigma transpose and U transpose. Agree? This is your identity matrix, this is orthogonal properties. Then what we can write remaining? U sigma transpose, agree, then U transpose. So, now what is this? This dimension is m cross n and this dimension is n cross n. So, this will be m. So, what you can write it? This you multiplied by this thing by U, both pre multiplied or post multiplied by U, then it is A transpose U is equal to U sigma transpose. Now, see, if A is a matrix, this whole thing is a matrix multiplied by the vector U is a matrix, each column then it will be a what is called, what you will get it, this one u into that I told you each element is only the diagonal elements of the, it will get sigma 1 square, sigma 2 square in this way. Okay. So, you know the definition of eigenvalue eigenvector. If A is a eigenvalue, A is a matrix, X is a, V is a vector, then this is the thing. So, using the definition of eigenvalue eigenvector, we can prove that statement of the first one. Similarly, we can say the columns of B n into n, this is V, n into n are the eigenvalues of eigenvectors of the matrix A transpose A, which is AH for complex AH A. Similarly, you can prove this one using that one. Okay. And third is the diagonal entries of sigma, the diagonal entries of sigma m cross n, the singular values of A m cross n, and it is denoted by sigma A, are the non-negative square roots of the eigenvalues lambda I of A transpose A or AH for complex is AH of A, which one is nothing but a sigma I is nothing but a square root of lambda I A transpose A transpose, or it will be lambda I A transpose A, agree, and I varies from 1 to dot p, and p is the minimum of m cross n. You see this one, if A, what is the dimension of A into A, first find out what is the dimension of A. It is a dimension of A is m cross n, and n transpose is n cross m. So, if m is less than n, then you will do this one. Okay. So, eigenvalues of square matrix is suppose n is less than m, then you do it this one A transpose A, agree? Then it will you will get the eigenvalues of sigma 1, sigma 2, all these things. That is why I have written P is minimum of that one, agree, that in this way that singular values you can find. Basically, if you see the structure of sigma, if you see the structure of sigma is like this way, sigma 1, sigma 2, dot sigma k, then 0, 0, then this will to sigma m, suppose it is m by m, and this is will be 0, 0, dot 0, 0, 0, 0, 0, 0, and 0, 0, 0, 0, 0, all are zeros. So, this is m cross n when I am considering m is less than n, but sigma 1, sigma 2, sigma 3, sigma k, after that it may be all are up to m may be distinct non-zero. Some of the may be 0. So, in general I am writing is k. So, in another is they are rearranged like this way, sigma 1 greater than equal to sigma 2 greater than equal to sigma 3 greater than equal to dot 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 sigma m. You can easily draw when n is less than m, this structure. So, this is the your that, and all sigma 1 sigma 2 all are positive non-zero or non-negative quantity up to this m, and using this structure we can find out the what is called the H infinity norm of a multi input multi output system norm. We know the H infinity norm of a system for single input single output case, it is nothing but a supremum of omega, agree, whether this is a real, agree, and what is the supremum value of this g of j omega, for this is for single input single output case, single input single output case. That means, you do the frequency response of this one, at what frequency you will get the maximum value of the gain, that is the H infinity norm of the system for single input single output. Based on this concept, we will see what is the H infinity norm of the multi input multi output system. Supremum means least upper bound. You can say the supremum is nothing but a least upper bound of this one. The frequency response of this one means gain, you gain at it frequency you see the gain, next frequency you see the gain, and over the sweeping the frequency from 0 to infinity, you see at what frequency you are getting the maximum gain, that is the H infinity norm of the system for single input single output system. So, we will stop it here, and next is multi input multi output system, what is the your H infinity norm, that we will see later, and based on this one H infinity controller also will give you the basic idea behind this, what H infinity norm of H systems. Okay, I will stop it here.